All right, line A6, we are in learning task number 1, where we are going to take a look at single-phase rectifier circuits. And there's some new phraseology that we're going to have over here, rectifiers and converters. And what we're going to be doing is utilizing one-way devices. Because we know that ultimately, whatever DC is, it is always going to be unidirectional. Now, DC can have a number of different waveforms. The DC that we most commonly think about is, flat line. DC is just going to be looking like that. That is going to be a rectified filtered type of DC. We've got other DC waveforms, and DC can take any sort of a waveform as long as it all stays above the zero and either in the fully positive or all of it stays in the fully negative. So something like this could be a DC waveform where it's going to be starting at 0, going up, dropping 0, up, like that. That would be considered to be a DC waveform. We could also have DC waveforms that are going to go and look like this. Once again, they're not crossing that axis. They're going all the way down to 0. We can have DC waveforms that are going to look like this, where it's not going to go even all the way down to 0. It's just going to be partially up top. And there's multiple uses for any one of these. Basically, any type of voltage, as long as it stays above the 0, is considered to be a DC type of voltage. Even this, irregular looking waveform would be considered to be DC. And that's what we're going to be doing, is we're going to be creating a waveform that is going to just stay on one side. We know that we have got the positive and negative, and that generally speaking, when we are looking at an AC waveform, we are going to go and spend half the time in either one of those two sides. What we're going to do right now is we are going to go and cut off one of the two sides, and then we're either going to go and just get rid of it entirely, or we're going to flip it over and put it back onto the other side. This is going to be called rectification. It's going to go and create what we refer to as a rectified waveform over here. Two main types of waveforms that we are going to have. We've got half wave. Half wave is going to have cut away and discarded half of the wave, right? What we see for a regular AC sine wave, we're cutting away and getting rid of all of that negative side of it. So that's going to be half wave rectified DC. And then full wave is going to be taking those halves that we would have thrown away before and then flipping them, sending them to the top over here, just through, doing some sneaky calculation, our connections, and utilizing our actual components. So full wave is going to go and have the same amount of power when we take a look at it as well, right? We see we get the whole waveform over here that we are going to be able to utilize. It's just now it's all going to be in the positive side. Okay, that is going to go and be my two main waveforms. Usefulness of these two waveforms really relies on the fact that they're going to be going down to 0 in a lot of cases, because there's going to be, in third year, you're going to cover a bunch of electronic devices that are going to go and shut off based upon minimum current, where we are going to be able to go and turn things on based on, what time that we want. So we could turn a waveform on over here, and then it's going to go and conduct, and then it'll automatically shut off once we hit a value of 0. So having these type of waveforms allows us to go with what will be referred to at that point as automatic commutation, or shut down, which means that we could go and have a blip through, and then we could just leave everything off, and until we give the next blip, we would not get any power out of them. It makes it a useful, controllable type of voltage. Sometimes we will also go and take what we've rectified, if we need to go and have a more uniform DC, and then we are going to go and filter out certain components that we are going to go and have. And all of these waveforms, whether they're going to be half wave or full wave, are going to be just reflections of what the sine wave was itself. This is going to be my peak, which is going to have been the same value as my AC peak that I would have had. If I have a 120 volt RMS waveform, we know that that 120 volt RMS has got a peak value of 170. My DC waveform would also have a peak value of 170 off of those ones. We're also going to go and have some new terminology that we are going to go and have. We are going to go and have V ripple. V ripple simply speaks about the height from the very top of my DC waveform to my very bottom. In this case, we're going to see that my V ripple is going to go and be this massive, value from 0 to 170. So I'll have a 170 volt ripple that I'm seeing. In some circuits, when we go and rectify them, rectification, and then we filter them, what we'll be able to do is we'll be able to go and curve off a little bit. Oops, sorry, that one's a bit wrong there. And for this type of a situation over here, what I'm going to go and have is I'm going to go and have a ripple voltage that is going to be much smaller, right? Between where the top of the waveform is and where the bottom of that waveform will be. We'll deal with those calculations later on as well. All right, let's talk about our first simple circuit, the DC half-wave rectification circuit. Now, there's a bunch of waveforms along the right-hand side that are going to be relating what we are seeing from my AC supply versus what I'm seeing at the load and what I'm seeing at the diode. First of all, you should be very familiar with this device over here. This is going to be referred to as a diode. You covered these inside of first year. If you don't remember what they are, go back and pull out your first year books and go back through that, because you need to know these components. They're going to be so critical. It's a one-way valve, basically. We've got two sides to it. Well, we'll just draw one out over here. We'll just start with a little bit of an intro over here. This is going to be my diode. This line over here is going to be called the cathode. This line over here is going to be called the anode over here. The way that I keep them straight inside of my mind is that this section over here that looks kind of like the top part of an A, that's going to be my anode over there. And then my anode and my cathode are going to go and have polarities that are going to be assigned to them. If I go and place a positive to the anode, then and a negative to my cathode, I would go into what's called forward bias. And forward bias means that this thing is going to go and pass voltage through, except for 0.7 of a volt. It always has to maintain, this 0.7 of a volt that's going to be over top of it when it's in conduction, and that's just the operational characteristic that we are going to go and have. We call it the forward voltage drop. If I go and reverse the value, or the direction of voltage, stick a positive there and a negative over there, then this thing is going to go and block. So we're always looking for us to have conduction. We're always looking for us to go and have a negative on that cathode. All right, going through into here, we've got AC input that we're going to feed in, and we've got a load over there. It's just going to be a simple resistive load here right now. My AC is going to go and alternate. So right now, I'm going to go and have a positive here and a more negative point over there. If I take a look at that, do I have a positive applied to the anode? Yes. Does my negative carry through to there? Absolutely yes. So this thing would have to be forward biased. So right now, as my AC is going positive over here like that, we are going to go and pass current through. So my current is going to be able to go and travel through the resistance over here and back out of the circuit. That's going to be when my alternation is forward like that. When my alternation reverses, and this goes negative and this goes positive over here, at that point we would have a negative applied to my cathode, or sorry, to my anode over here, a positive applied to my cathode. We would be in blocking at that point, which would mean that I'm going to get no current flow that is going to go over here. And what we would see is we would see this source voltage, the negative side of the source voltage. If I had a voltmeter, that's what they're looking at over here on this little drawing. It's just having a voltmeter and saying, this is what I would be seeing on the voltmeter over the top of the diode. This is what I would be seeing on the voltmeter that is going to be over top of my load, would be that one over there. Really, these voltage waveforms that are over here on the sides don't get too bent out of shape over top of them. It's a bit confusing in the layout, the way that they have them over there. They're showing that, what they're really just trying to show is that, look, we take an AC waveform. We're only going to go past half of that waveform through to the load. The other half of the waveform, we are going to be blocking with the diode over there. They show you the reverse connection, if they would take and flip around the diode over here, and then this diode is going to once again act as a one-way valve, but now it would be able to go and pass the negative through. So we would be able to go and get current flow in the opposite direction through our load. In other words, our load would now be able to see the negative current, and then we would go and block off with the diode the positive side of that alternation. It's just a flip around from this side over to the other. That's all the difference is between diagram number 1 and diagram number 2. It's going to be looking at that direction of polarity in the diode, and that's really going to go and redefine what I can go and place through my actual load itself as far as direction. Talking about values that we are going to go and have on here, peak and PIV are two that we need to know about. Peak values is obviously going to be the peak value of voltage that's going to get passed through to this load over here. Now, if I take a look at this load, if it gets my full value through here, it is going to be the full peak of what my AC would have been itself. So if my AC was 120 volts RMS, we can take an RMS value, we can divide it by 0.707, which is going to get us to a peak value, which is going to be 169.8. We round that to 170 volts. So we've got 170 volts. That is going to be the absolute peak that I'm going to go and see at my load over here. What about when this thing is reverse biased? When I've got a positive up here and a negative over here, and therefore I've got a positive over here and a negative over here, and this is going to be a blocking diode. How many volts does that diode need to go and block? Well, my diode needs to go and block the opposite peak, right? That's what it's doing at that point, would be blocking that. So it is going to go and have to block for 170 volts. This leads to a new value that we haven't had before that is going to be referred to as my PIV, or peak inverse, or that means opposite voltage, that we are going to go and have. The PIV is going to be a rating that you need to have on all of your rectifier circuits, and it always needs to go and match. For these ones over here, for a single phase halfway rectifier circuit, it needs to go and match the peak of my AC. It's only ever blocking one peak at a time. You see that down over here, there's only ever a single peak it's blocking at a time, so it only needs to be matched for a single peak. Okay, let's take a look at this one over here. The next one that we are going to have is going to be a full wave rectifier circuit. And this one is going to be what we refer to as a biphase type. Now, the biphase type of rectifier has got some benefits over top of the next rectifier we're going to look at, which is going to be the bridge rectifier. The biphase does have only 2 diodes. The full wave, which is the other way that we can do this, is going to go and have 4 diodes inside of it. So the full wave requires more diodes that are going to be utilized inside of it. But my biphase also requires the use of a transformer inside of it. Now, in a lot of cases, we are already having to step down from our line value voltage, 120 volts that we have, RMS coming in. We're usually going to be stepping that down to a lower value voltage to operate our DC, because a lot of our DC, excuse me, is going to go and operate off of what we refer to as TTL levels. TTL, it stands for transistor logic. That's going to be 0 and 5 volts generally. We do have some CMOS levels as well that will go up to about like 12 volts, but most of our electronic components will be down inside of that 5 volts when we're looking at them as electronic actuations. If we're looking for DC power is going to be, like 24 volts in a lot of cases that we're going to be utilizing for contactors and, small motors and things like that. So it depends on what your application is, but most cases you will be dropping from line voltage, VL, down to TTL values or down to 24 volts. So in a lot of cases you need to have something that can drop that value anyways. This transformer is an expensive component. Not like expensive like the way of buying a car, but if I'm a manufacturer that's going to build 100,000 units of some piece of equipment, I don't want to necessarily have to buy transformers if I don't need to. So we do use these ones where we have to drop the voltage anyways. We will go and utilize them. There is another methodology that we can use with these, the semiconductors, the diodes, that I can go and attenuate or chop off, these peaks later on. That's more complicated electronic theory, and that's something that we don't really deal with over here inside of our, job as construction electricians. So we're going to leave that one alone, but, there is a way that I can come in at line voltage over here, 120 volts. I can rectify that through here, and then what I have is I've just got an additional section before the load that would then go and chop down that voltage into something that's going to be usable. It's cool, it's usable. We won't cover it because it's not necessary for what our understanding is. We're going to go back to this one, do the explanation on it here right now. So this is going to go and be my full wave biphase transformer that I'm going to go and have. We see that there's going to be a single diode that's going to be over here. We're going to see this transformer over here as well. Once again, remember that for every action, there's an equal and opposite reaction. I can never have a positive without having a negative. So on a transformer, that means if one side is positive, the other side here has to be negative. Let's make this a subtractive transformer. We'll stick a little dot here and a little dot here. That means that whatever I have got on this side is going to have to be the same as what I'm going to have over here, right? So if this is currently negative, that would mean that this side would have to be negative as well. If this side is negative, the opposite end of the transformer would therefore have to be positive as well. And if this side over here is negative, in reference to that negative, this section over here would have to be a slight bit more positive. And in reference to this positive, this end of this winding would have to be a slight bit more negative. It's our neutral point, that weird, positive type of thing that we see going on there. Taking a look at the polarities that I've just drawn in here right now, we should note that these polarities are going to, I don't know why I drew that negative sideways, are going to go in forward biased one of my two transistors. Let's go and take a look. We got a positive over here that is attached to a cathode. Therefore, this one is going to go and be blocking. Draw a big red line through that one. And if I go down here to the bottom, I see I've got a negative attached to a cathode. Therefore, this one is going to be passing current. So if I want to take a look at the current right now, I can see that this winding over here, this winding is an electrical source. So the current is going to flow out of it. I'm going to pass current through here. The current gets up to this junction. Can't go there. That's an open circuit, right? It's a blocking diode. So my current is going to go and travel through here. And then it's going to be able to travel all the way back up through here. Only this side of the transformer is going to be active. Right now, the other side is going to be blocked. There's an incomplete path. We'll have no current flow through that top side because this diode over there is blocking that off. So we get that, one of these is going to go and conduct. What happens is my AC alternates and all of my directions of current are going to go and change. So I'm going to go and just erase all of these. Ooh, I need to keep that transformer polarity dot over there. So now we are going to go and have our positive down here, our negative up there, and if that's what I've got, my positive would therefore have to be there, which would mean the opposite end of my transformer would have to be negative. And if this section of this end of this winding is positive, this end would have to be a slight bit more negative. And if this end of this winding is negative, this end would have to be a slight bit more positive. Once again, I'm going to go through my diodes, and I'm going to say which of these is blocking, which of these is going to be good to go. Well, I take a look at this bottom one down here. It is a positive that is attached to a cathode. Therefore, this one is going to be blocking. I go up top over here, and I see I've got a negative attached to a cathode. Therefore, this one is going to go and be conducting. And so now, I'm going to be able to pass current out of my transformer. Transformer is an electrical source. Pass out of that transformer through that diode. That current isn't going to go down here because that's blocking. There's no complete path, so it's going to just pass through here. Going to come back along that line over there, and then it is going to go and travel up through there. We've got a complete circuit over here, complete path for current. We see that once again we have driven current through the load in the same direction. That is what full wave rectification is going to go and be, is that we're always going to be looking at driving current through the load in the same direction. Over here they're showing us, diode 1 conducts, diode 2 conducts. Diode 1 would then conduct, diode 2 would conduct. They would alternate as they go through here. If you were to go and reverse either one of these diodes, you do run into massive problems. Like if I stick this one over here like that, that would mean that at any point where my transformer is positive, negative, positive, negative like that, I would have both of these diodes that would be forward biased, and so what I can get is I can get current that would then travel through like that. We would end up with a direct short circuit. What we're seeing on these is always, always, always that those diodes are facing in towards that little transformer that we are going to have. Peak inverse voltages are also going to be needed to be calculated for these ones. Once again, if I give my polarity dots over here, we will go with the positive here, which would mean this is a positive. Therefore, this point is a little bit more negative. This point is going to be negative, and this point would have to be a slight bit more positive over there in the neutral. So looking at these, we're just going to take a look at which ones of these are going to be forward biased and which ones are going to be reverse biased. I see I have got a negative attached up here to a cathode, so that one's forward biased. I see that down here, I have got a positive attached, so this one is going to go and be blocking. And if I take a look, I do have voltage that is going to be impressed across these secondaries, right? Just because there's no current flowing doesn't mean that there's necessarily going to be voltage. But if I were to take a look at it, I could see that I'm taking this negative here. We're going to flow current through there out to that point. So we're going to pass that negative through to there. As far as voltage goes, I can see I'm putting that negative all the way through to here. And then if I follow the rest of this path through here, I see that I'm going to be placing that positive all the way over here. In other words, that diode is blocking that complete path that we are going to have over there. So what do I need to go and have for my PIV rating for this one? Well, I need to go and have double the value of one of these. Let's say that each one of these was rated for 24 volts DC. That would mean 24 plus another 24 would be a grand total of 48 volts that I would need to have. That's going to be my RMS values. I would have to take that 48 divided by 0.707, and then that would go and give me my actual peak value. I can't do that math in my head. We'll have to use the old calculator for that. 48 divided by 0.707 gets me to a value of 68. So I would need to go and have something that would be good for 68 volts PIV rating on this one. The other one would be the exact same because they just, take turns passing through. So you're going to have to take turns blocking that whole value as well. You do need to go and double the individual phase value. That's what it's going to be. This is going to be referred to as a phase. This is going to be referred to as a phase as well. If you figure out what that phase value is, double that thing, and you're going to be good to go. The other way that you could say is that it has to be good for the peak of my line-to-line voltage from there to there. Okay, let's talk about this one over here because this is our most common type that we are going to have. This is going to be a full wave bridge rectifier over here. Full wave bridge rectifier, sometimes also referred to as a H-bridge. Do not refer to this thing as a Wheatstone bridge. That is something from first year that you would have covered, and for some reason everybody just loves that word, Wheatstone bridge. Wheatstone bridge is a setup of resistances connected in the same manner over here, but it's to do with resistance, so it does not apply over here. This is a bridge rectifier. A bridge rectifier is going to go and have pairs of diodes that are going to work in tandem together to go and pass current through. And they give us a very great visualization of that. They actually cut away the ones that are not conducting. So these diagrams that they have over here, the conducting pairs, is this diagram over here. They're just ghosting the other ones that we would normally have across here and here. They're just not showing them so that we don't have to kind of analyze them at any given point. But it's showing that, look, when we've got a positive over here, I'm going to go and have a positive here. This is going to be forward biased. This one will be forward biased, and I would be able to go and pass my current through here in that direction. And then it shows that, look, when I go into the next half cycle of my AC, where I alternate, I'm going to go and have now this one that is going to be forward biased, and this one that's going to be forward biased, and I'm going to be able to go and pass my current through to there. So I'm going to, once again, carry the current through in the same direction. This is how we deal with, full wave rectification. Full wave rectification is just us taking the current and through tricky connections, forcing it through the load, whatever that load is going to be, always in the same direction. That is one common way that we are going to go and draw these things out. Another method that we are going to see, besides this one, is going to go and be where it's drawn here as an alternative schematic like this. And then there's one other schematic that they don't draw over here, but you'll hear it pulled or talked about quite a lot. It's going to be called the H-bridge. I'll just draw you the H-bridge over here for a second. H-bridge is going to go and have my components drawn in as being a line to line, and then I'm going to go and connect my load across the center. See how on this one over here, they're connecting across the center? It's a more commonly drawn designation where I'm going to go and have my diodes going through. Like that. That, I should actually remove that because that's where my load itself is going to go and be. This is what you'll commonly hear referred to as a H-bridge. When you look at the H-bridge circuit, you should be able to identify that this thing is basically the same as this. We've just straightened these bars out. Instead of drawing them as a little triangle over here, we are now drawing them vertically like that. But it's just become a more common method of drawing them just because it's easier to draw. It's a straight up and down. Same deal as what we had before. We're going to go and have alternate conduction, right? If I got a positive, negative there, I would see that this one would be conducting because it's got a positive to the anode. This one would be blocking because it's got a positive to the cathode. And if I go down here, I see you got a negative to the anode. So this one's going to be blocking. This one would be conducting. And therefore, I would go and have current through in this state. It's going to go and travel through like that over there. And then alternatively, when I go and change my alternation, this one here now becomes my negative. This one here becomes my positive. What we're going to do is once again, the positive gets applied. This one here is now going to be the one that will go and be forward biased. This one would be reverse biased. Up top over here, this one would be forward biased. This would be reverse biased. And then once again, our current is going to go and travel through the load like that. So this configuration over here, what they refer to as the bridge type, is commonly referred to as the H bridge. If you take a look at it, it looks like an H. 2 diodes face in, 2 diodes face out on there. This other configuration that they draw here, why don't I just erase this one first, and we'll redraw that one, or we'll take a look at that other one. Is a valid configuration as well. It's just looking at it a little bit different. You need to be very careful with these types of drawings over here that you do not connect. If you're making drawings, that you don't place the AC in on the DC side, because if you place the AC in, you're going to go and end up with a dead short off of these things. Note how all these diodes are going in the same direction, and that I'm coming into the center of the diodes over here, and then I'm passing out to these. Same deal as before. If we go and place a positive and a negative, we can always take a look at these and say which of these are going to be forward biased. That positive goes onto this line rung over here. It is going to be passing through there. It would be blocked by there. This negative gets placed onto this rung here. It is going to be passing through here. It is going to be blocking through there. And so therefore you would be able to go and drive your current through, up, and in that direction. And you can follow the same thing out for your opposite alternation. You should do it yourself. I don't need to draw it out for you. You are all quite capable of it at this point. A couple of things I do want to highlight on here is these colors that they're giving us over here. These colors are going to be ways that these are going to be identified in the field. In the field, it's seldom that you're going to go and buy individual diodes and you're going to go and connect them. Usually, what you will do if you are doing rectification is you're going to go and buy what we refer to as a phenolic package. Phenolic is a fancy way of saying non-conducting plastic that we are going to go and have. And a phenolic package is going to just have leads coming off of it that are going to tell us what we need to go and identify them as. I'm going to draw a couple of different phenolic packages over here. So one of these phenolic packages is going to look like this. Now usually they're going to be kind of a metal canister. It's usually going to have a hole in the center so you can drive a screw through to go and drive this thing down to whatever the substrate is going to be. You're going to go and have leads that are going to come out, or they're going to go and have those bayonets that are coming off. Those little blade types that you use with those stake-on types of connectors. In the field, excuse me, these are going to be identified. There's going to be a yellow dot and a yellow dot, and then there's going to go and be a red dot, and then there's going to go and be a black dot on there. This is just going to identify the yellow dots are always going to be the AC. Note how these are yellow over here. The red is going to be the positive DC plus that we see over there. The black is going to go and be the negative DC. That is one way that they go and identify them. Other ways that they are identified just redraw it actually because I'm having trouble erasing just the components I want. Other ways that they will go and be identified is going to look more or less the same, but it's not going to have any dots on it. You're going to have a blade, a blade, a blade, and then you're going to have one blade that's going to be at 90 degrees. That is going to be your identification that tells you that that one must be the positive, and always kitty corner would therefore have to be the negative, and then these ones over here would have to go and be your AC. Sometimes on the package, what you'll also have is you will go and have a sine wave, and a plus and a negative. That's relatively easy for you to identify. The sine wave is going to be the AC. Connect any AC polarity onto it, right? Doesn't matter, your two lines go onto there, your positive and negative go over there. The other method that is sometimes used in identification on these ones is going to go and be what we refer to as a clipped corner. So that's going to be one corner that is going to be truncated. It's going to be clipped off at 45 degrees. That truncated corner is going to go and be my positive. It's usually the most important thing to go and identify where the positive is going to be, because we're going to be connected into DC devices, and we don't like to put those things onto line backwards, right? That destroys stuff. So what we're looking for is always going to be, where's my positive? The positive is going to be identified with a plus, a red dot, a clipped corner, let's put in CC for clipped corner, or it is going to go and have a out of alignment. That is going to go and tell us that it's going to be the different one. You will be able to identify these things in this field. They're about, usually most of these cases are going to be no more than about 1.5 inches by 1.5 inches. They're relatively small components that are just going to be screwed down into the back of the cabinet, and we just tie our leads off to these things. Let's talk about our value of PIV rating that we are going to need to have. Our PIV rating that we will need to have is going to be based upon what we're going to be blocking at any given time. Excuse me. If I take a look at my line side feeding in, either on here or on my other one, what I can do is I can just verify that I'm only ever going to go and have a single one operating at a time. So just disregard this ohm meter here right now. We don't need to see that ohm meter yet. We will see that ohm meter in a minute. But let's go and talk about PIV rating for my diodes. If I've got a positive over here, this one would be conducting. This one over here is going to go and be blocking, right? And if I've got a PIV or a negative over here, this one is going to be conducting. This one over here is going to be blocking. I'm going to just trace around my voltage right now, looking at my actual value of voltage that is going to be coming into here. I see that there is a path where this thing could come up to there, and my voltage could come up to there, right? So I'm going to cross it because we see that this thing is going to be, it's a blocking, it's a reverse polarity here right now, but it has to go and block that. So what value do I have? Well, if I've got an AC value that's coming in, remember that we can't actually see the line to line at any given time, right? Only this is active or only this is active at a time. So what I'm going to be blocking right now is I'm only blocking one of my alternations. If I've got a 120 volts AC waveform, that means that each of these sides is going to be a peak value of 170. So this over here needs to be rated for a peak of 170. Whatever my AC values are feeding in, I just need to go and convert that to a peak to get my PIV ratings for these ones. There is a ohm meter that is going to go and be shown over here as well. The ohm meter is to do with testing of these ones. And what we're doing with this testing over here is we're forward biasing, and we're going to be checking to make sure that I don't have any of these diodes that are placed in here incorrectly. If one of these diodes is placed in here incorrectly, we'll start with this one over here. What's going to happen is my ohm meter puts out a small value of voltage. That's how an ohm meter reads. Is it puts out a small value of voltage that it knows about, and then it reads the amount of current that goes through the circuit, and then it does the math inside of its little ohm meter brain that says, I put out this many volts, I had this many amps flowing back through it, therefore the resistance that I'm going to display for this electrician here is going to be, this many ohms. It's doing that all inside of itself, but it means it does have a positive and a negative. That's coming off the battery that's inside of your ohm meter. So if I take a look at this, right now we'll go with the solid black lines right now. If I got a positive over there, I would see that this one would be forward biased, and I would see that this negative down here would mean that this one would be forward biased as well. But in this case, because I got a bad diode connection inside of here, it would be forward biased as well. So I would be able to actually, from my ohm meter over here, dump currents through, right? Take a look at this. We would see that we can go through here and back up to there. That is going to go and tell me that I've got a diode that's misaligned. So when I'm doing my testing, what I want to do is I want to just take my ohm meter and I want to go and place it across. I want to try it on here, and then I'm going to flip my leads. I'm going to try it in the opposite direction, and I should read infinity in both directions. If I read anything smaller than infinity, I'm going to double check my connections. But infinite ohms in both directions, because there will always be a blocking set of diodes. You do also have to do this with nothing attached at the load. If you try to do this test with your load already attached, you will be driving some of your ohm meter current through your forward bias diode. So I drive a little bit through here, and then I would come back over here on that one, which would mean that I would get a small amount of current going through there, and I would be measuring that as well. So always do this with the load side disconnected. Okay. Last thing that I want to go and talk about is the polarity of these things when we actually connect it. If I have got a Wheatstone bridge, a bridge rectifier over here, and I connect that thing in backwards, bad things are going to go and happen. Remember, this is the same one. We have this one over here. They show that's got the yellow and the yellow, the red and the black. But if for whatever reason I was like, well, red is my line 1, that must be line 1, and black must be my line 2. And then I'm like, well, I don't know what these yellow leads are, but one of them will be positive DC and the other one will be negative DC. I'll meter that out afterwards. If I connect AC onto here, I'm going to be fine for half of an alternation. Basically, when my line 1 is positive, line 2 is negative. So if I take a look at that, I would see that I would be blocking right now. But as soon as my AC alternates and my line 1 goes positive, my line 2 goes negative, at that point, oops, sorry, that's what I just did there. This one goes negative and this one goes positive here. At that point, I'm going to see that I would be able to pass current through a forward biased diode. That one's got a negative, it's going to be forward biased. This one's got a positive, it's going to be forward biased, and boom, I've got current that can travel through there, as well as I've got a second parallel path, just in case the one short circuit wasn't good enough. I've got 2 short circuits over here, so I can get, a dramatic explosion and the smoke gets out and things like that. It is not something that you want to go and see. So make sure when you're hooking these things up, you do not connect it backwards. If you connect it backwards, guaranteed destruction of your components and a short circuit that is going to be on there. Let's talk about the waveform that we are going to get out as well. Our waveform is going to go and have a ripple. We've talked about that there's a ripple voltage and there's also going to be a ripple frequency. Frequency is from where a waveform starts to where a waveform starts again, right? So for a regular 68 hertz waveform, we see that we are going to go and take 16.66 milliseconds, and then that is going to be able to be inverted. So that's my measurement that I have. That's where we get frequency from. You should remember this from first year, I'm hoping. But we take our time, 16.6 milliseconds, so 0.0166, just round that off to 7, well, this one wouldn't be milliseconds, this would be seconds because we're writing it out as milli over there. That's the amount of time it takes for me to go and start and get to the point where I'm starting another waveform. And so what I do is I take that time and then I go and invert that to the -1, and that's what spits out my 60 hertz, my frequency. If I take a look at a half-wave rectified circuit, my half-wave rectified circuit is going to go and have a hump and a line. And then it's going to go and have a hump and a line, like that we are going to go and have, right? It's just going to be this total amount of time. This is where this thing starts, right over here. This is where it starts to repeat itself. What's the length of time it takes? Well, it's going to go and take that same 16.6 milliseconds. Therefore, it's going to have the same frequency. If I fed in 60 hertz AC, my half-wave rectified is going to come out as 60 hertz half-wave rectified DC that I will have. If I go to full-wave rectification, we go from where we start to where we start to repeat ourselves. At this point now, because we're flipping that over, we are repeating ourselves after 8.3 milliseconds. So we are going to go and take that 8.3 milliseconds, invert that, and then you are going to go and find out that you're going to have a doubling of your frequency. You're bringing that up to $1.20 over here. Okay? It's like Mr. Zoggs. It is just quick hump after another, after another, after another that we're going to go and have through here. Whereas this one, it's hump and a line that we're seeing through these ones. Okay, that is it for learning task number 1. That's going to be your rectification. Go through and check that self-test. There's some interesting stuff inside of there, to do with them utilizing ground paths to go back through there, as well as with them utilizing some testing diodes inside of it.